How about now? Okay, so sorry about this. It is a really fiddly business with the live stream, and I've not done one for a while. So let's get going with it. So again, sorry about the link change. I'll just wait just a minute in case anybody else couldn't find the link. So again, if these people find these useful, we can do some more over the holidays. And again, it might be useful for some of you to watch last year's live stream as well, because it goes over the same lecture notes. So let's just get on to it. Alright, so we're just going to cover some of the topics from the first 4 lectures. So I sent some rough slides out for you to look at when we go through. So again, these are just a sketch. I'm going to add on to them so you can make additions as we're going down. So we're going to just have a quick recap of MAQ processes. So again, we didn't derive this in lecture, but there are video clips on this. But again, it might be useful if you've got any questions, we can go through them. So again, let's just recap the MAQ model. So again, it's just a definition. So any process, call it YT, which looks like this, it's equal to a constant plus some weighted average of these Q shocks, where the weights are given here, and we normalize theta naught to 1. So you can think of theta naught as the coefficient on epsilon t. So you could think of having theta naught epsilon t in general, and we've just normalized theta naught equal to 1. Otherwise, you wouldn't be able to identify this. We wouldn't be able to separately identify this. So we normalize this to 1 so we can estimate the other coefficients. So in a way, you can think of the theta 1 as a relative weight to theta naught. Given we've normalized theta 1, then all the other coefficients technically can be thought of as this. So they're the relative effect. Again, we assume epsilon t is a white noise, and you need to be comfortable with this definition. So again, it's mean naught every time period, constant finite variance every time period, and it's got a covariance function which only depends upon the size, the absolute size of the gap between the observations, not the time period that we're at. So you need to be able to show all 3 of these results. So they go forward in order of difficulty. So the mean's relatively straightforward to derive. So we can just use the above. So we just take epsilon, we can go back to here and just take the mean on both sides. So again, we have E of YT, plug in the above, and again expand it out. So you would do the whole, don't start there. Okay, you plug in YT from the definition of the MA, and then we just expand it out. So we use the additivity property of the expectation. So the expectation of the sum is the sum of the expectations, and all constants come outside. So equals alpha plus expectation of epsilon t plus ... theta q expectation of epsilon t minus q. Again, so and by white noise 1, so you need to state what it is, but this equals alpha by the white noise 1 assumption, going back to the lecture notes, namely that E of epsilon t is not for all time periods. So that's relatively straightforward. A common exam type mistake is to say that epsilon t minus q equals naught as opposed to the expectation. And again, so always think about this. We're not saying that the actual shock itself is naught, we're saying that the average of the shock is naught. So epsilon t minus q is some random variable. It could be, say, a normal 0.1 variable. And we're just saying that it's on average, if we kept drawing it again and again and again, the average of the value would be naught, not the actual level itself. And again, if all the shocks were naught, then of course it would just be a deterministic process. We can do the same thing for the variance. Again, you can expand this out. There's 2 ways you can do this. The lecture notes go through a more, I think they do the more detailed way. But you can just use the general result for the variance. So we have variance. So again, I think I've gone through the longer way in the class, but as a quicker way of showing it well, we just plug in alpha plus epsilon t And so the alpha is a constant, so that won't affect the variance. Again, if you add a constant to any random variable, it will not change the variance because it's a variation around the mean. So if you add a constant to a variable, it changes the mean by the same amount, and therefore the variance will not change. Again, the variance of the sum, because so you need to make clear that this equals variance of epsilon t plus variance theta 1 epsilon t minus 1 plus, and the next step follows by the uncorrelated assumption. So this follows because the shocks, again remember this upside down means because epsilon t are uncorrelated, and this follows by white noise 3. So that's a general result, that the variance of the sum of any, if you have one random variable, that's a sum of some other ones. If all the variables are uncorrelated, then the variance of the sum is a sum of the variance. And you've seen this expansion from before. You'll have seen something like this before. Remember, a general result as an aside, the variance of ax, where x is a random variable, plus some constant b times y, where y is a random variable, is a squared variance of x plus b squared variance of y plus, and do that as an exercise. You should be able to establish that from the. So this would be this is the general formula for the variance of some weighted average of two random variables x and y. So this makes no assumptions here. So if the covariance is not, then of course it simplifies and this last term drops out, and we just get the sum of the variances here, because this is just the variance of ax and this is the variance of bx, where of course the a comes out squared here and the b comes out squared. We can also see that from the formula. You can show that yourself, because the variance of ax, well, just use the general formula. It's e of ax minus e of ax squared, and you can see straight away that a just comes out, so this just equals a squared, because a is constant, e of x minus e of x squared, and this is just by definition the variance of x. So this is just a recap really of relatively basic statistics results, so you should be quite comfortable with this. You should be able to show this as well. You can do the exact same thing, do something like this. We can use a general formula, expand it all out, and you can show all this. So the next step then, we've used a general result on the variance function. Yeah, so you can use the quick method. The key thing is that you detail all the steps. You make it very clear why we can go from one step to the next and under which white noise assumption that it is. So yeah, that's key for any, as long as you make clear why, then that's fine. Then we can go down here, and then these come out because they're all constant, so we're going to get theta 1 squared and then that's it. So then the last one is going to be what? Well, it's going to be the final the second white noise assumption, that all the variances are equal to each other. So again, the variance of epsilon t is equal to the variance of epsilon t minus 1, and all the way down to variance of epsilon t minus k, or q, sorry. So this is it, and then it'll come out. So we can take sigma squared out, and we're going to get 1 plus theta 1 squared plus theta q squared, and this holds by white noise 2. I need to state what that is, that the variances are, so this is by white noise 3, this is by white noise 2. And again, you'd state these in your answer what they are. You need to state them first, but we just use the notation we used in the lecture. We can, if we want, write this in its summary form, so we can write it out like this, or you can summarize it. We can write this in its summation form, and again, you can just choose the index. You can call it S, say S equals 0 to Q of theta S to the Q. Sorry, yeah. Okay, and this works again because remember theta 0 is just 1. So when we expand it back out, these two are going to be equivalent to each other. So you can write it in either way, but if you see it in this form, don't get confused, it's just summarizing this here. When we expand it out, we get back to the above. So deriving the mean is relatively straightforward. The variance, you're just using basic variance operators. And then the trickier part is deriving the covariance function. But because we know that all the shocks are uncorrelated, when we look at yt and yt lagged back a number of periods, we just need to find the concurrent shocks. And every time you lag back yt 1 then 2, you're going to keep shifting along. You're going to shift along, and there's going to be, in essence, if you're at yt minus k, well, there's going to be q minus k common shocks. If k is bigger than q, then there's no common shocks, because yt and yt minus k, where k is bigger than q, will not be correlated. So we run through this, but again, we're now going to show this. And when you derive the covariance, so that, remember, this is just shorthand for the covariance of yt minus k. When we ask for the autocovariance function, we want the whole function for every value of k. So we've already derived it for k equal 0, which is just the variance. When k equals 0, we get back to this. We can see for k equals 0, we're just going to get sigma s equals 0 to q of theta s squared when k equals 0. So we need to derive the rest of it now, k equals 1 to q. So you can see straight away, for k bigger than q, there can be no correlation of yt and yt minus k when k is bigger than q, because there'll be no common shocks between the two models. So we can use what's called the tabular method, which is given in the slides. So let's start. So we've seen already, we can already motivate that there's only going to be correlations between k less than or equal to q. We've already got it, we've already done k equal 0, so now we need to find the rest. So we can see that the only non-zero correlations are going to come potentially between k equals q and 1. For k bigger than q, we're going to be pushed back, and there'll be, for example, if we have yt minus k, it equals alpha plus epsilon t minus k plus, and it goes back. If k is bigger than q, we can see straight away yt minus k is only going to be a function of shocks beyond epsilon t minus q, and they're all uncorrelated with each other. So you need to know, that's the key, that for this kind of problem, that's the key thing to know. Technically, you've got to find an infinite number of covariances, but obviously an infinite number of them are all going to be equal to 0. So technically we've only got to derive q, and they'll all follow a similar pattern. So let's start with deriving at k equal 1. We've done k equal 0, which is a variance. Let's do k equal 1, which I think clearly shows the idea. Well, firstly we need the general formula, which is e of yt minus its mean, which again is alpha from before, times yt minus 1 minus alpha. And again, you need to state where this comes from. You need to make it clear. You'd give the general formula first, and then it simplifies down to this from before. So again, this would have been e of yt, and this would have been e of yt minus 1 here. Well, we know what yt minus alpha is. It's just this part here. So we've written it like this. So we've taken yt, this part. Let me get a, how do I do a box? We've broken it up, and we've written yt minus alpha on the top, and we've written yt minus 1 alpha underneath, just to make it clearer to view. You're still just multiplying one by another. So this here, this isn't going to work. So this part, where's the box? Okay. So this top part here is just e, this is just yt minus alpha here. And then underneath, it gives yt minus 1 minus alpha there. So this is yt minus alpha. We can get that from the general formula before, and this is yt minus 1 minus alpha. And we can see, well, we can see yt minus alpha again. It's just a function of the shocks from epsilon t to epsilon t minus q. We can see for t minus 1, all it does is just shift us back 1, and now it starts at epsilon t minus 1. So technically, if you think of this would be theta naught, which is normalized to 1. It's just pushed us back 1. And then we can see that, well, only the only correlation is going to be driven, potential correlation is going to be driven by these common shocks here, here, and here, all the way down to here. And again, this last one's pushed us along 1 now, so this will not cause any correlation here. So we can see then, well, what's the gap between the end one and the first? Well, it's just t minus q minus t minus 1. We can see there are q minus 1 terms between t minus 1 and t minus q. And that's it. And when we multiply all this out, all the cross product terms are going to be naught. So again, you need to make clear that this was by white noise 3. You don't actually need, obviously in general you can't expand everyone out because it's for a general Q, but you can make it clear that only these terms selected, only the terms parallel to each other beneath like this are going to come out with a non-zero expectation. When we take the expectation through, then we're going to get out this term from here, this term from there, and then all the way to the end here. So is everyone clear on that? So then we can see then we've got q minus 1 common shocks, and we can see that makes sense because we've shifted along 1, therefore there's only one term which now no longer drives a correlation, this e epsilon t minus q minus 1. And then, so this is by white noise 3, want to expand this out, and then of course we can take the sigma squared out, and this follows by the white noise 2. And we get down, just writing it here, we get the beneath. So we've done it for lag 1, and then when we do it for lag 2, you can see straight away what's going to happen. Well, looking at, just, you should be able to visualize this. When you do 2, now you're going to knock, go back to here. Now when you shift it again, you're going to knock two shocks out. So there's going to be q minus 2 shocks that are left that could be correlated. And then again, you just work out the coefficient. And now the gap between the theta's subscripts will be 2 as opposed to 1. So think of this as theta naught times theta 1. The gap between the subscripts is 1. Now the gap is going to be 2 between them, and there's going to be 1 fewer of the terms to add on, because now we've knocked out another of the shocks. So now you can now you can do it for all the rest of them. So we've done k equals 0 and k equals 1. Now for the remaining k which are less than or equal to q and bigger than 1, we can work out the rest. So now, again, we've got yt minus alpha on the top and yt minus k minus alpha on the bottom. So again, you need to write out all the steps before. This is just the crucial step where you're picking out the key terms. So you'd write covariance yt minus k to give the definition. You know the means are alpha. Then you've got down to the top. Then you substitute in yt minus alpha and yt minus k minus alpha, and then you compare the coefficients. So now you can see, now all we've done is really push us back. Sorry, that should be a k there. And that should be a k. So sometimes I did it for j or k. So we can see now pushing it back k times. So now yt minus k is going to start at epsilon t minus k and then go back q lags. So it's going to start epsilon t minus k and end epsilon t minus q minus k. So now we need to pick out the first of the common shocks. So we know that epsilon t minus k in yt has just got coefficient theta k. So again, we've got theta 1 epsilon 1, theta 2 epsilon t minus 2, ... theta k epsilon t minus k in yt. And go back, well, the only terms that are going to be concurrent is going to be up to epsilon t minus q, because after that there'll be no common shocks. So just like we just did q equal 1, now we're doing it for general q. So only up to t minus q can there be occurrent shocks. And here we've gone back, well, what's the gap between t minus q and t minus k? Well, it's just q minus k. So we've got t minus k is the starting point, and where we end at t minus q. So we can work out how many we've added together, and therefore we can get the subscript on theta. The subscript on theta just being how many shocks along we've gone in the MA, and this will just be Q minus K. Just like we had Q minus 1 before. So is that clear? So it's kind of quite abstract, but you should be able to pick out this. And then, so again, this follows by the white noise 3 because all the rest are uncorrelated. And then, again, we can take out sigma squared and we get down to here. So this is for all K less than or equal to Q and K, well, technically it's for all K, but again, we've just done it for, the general formula works with K equals 0 and K equals 1. Sorry, anyway. Yeah. So, well, we've done, okay, we've done K equal 0, K equal 1, and then this is the rest of them. On the next slide, we'll give the general formula, which will collapse for all of them. So we've got K equal 0, K equal 1. We can see what's going on here. We've got the sum now of there's Q minus K terms in here, and the gap between the coefficients is now K for each one. So you can always tell whether or not you've got the answer right, because there should always be Q minus K terms. That's the number of concurrent shocks between YT and YT minus K. And then we can see, because we shifted back K, the gap between them is going to always be K between them. So we can now summarize this and put it in this form here. So this is what we've just shown, basically. So then it's the sum, there's going to be Q minus K terms from S equal 0 to Q minus K. When we expand this back out, sigma S equal 0, Q minus K of theta S plus K is, well, for start S equal 0, we're going to get theta K plus, and then we're going to get theta 1, theta K plus 1, plus dot dot dot, and go all the way back and to Q minus K, and then we're going to get theta Q minus K times theta Q, which is what we had before. It's just this here. So this is the general formula for any case, but for any K. So there'll be Q minus K terms. For K equal 0, this will give us back the variance, and so on. So hopefully that was clear. And then again, for K bigger than Q, and again, you'd need to say Y in your answer. For K bigger than Q, then there are no concurrent shocks using this tabular method, and therefore all the remaining covariances will be not. To get the autocovariance function, well, for a stationary process, theta K, the correlation function, is just the covariance at K divided by the variance, which we can write as gamma naught. So don't get confused, this is just the same as this, it's just using a different index. This one here has just shifted us forward K. So we can show that theta, if we take the theta S equal 0 to Q minus K. So it's just showing you you can write the name of the index is irrelevant, really. If you take theta S equals K, if you add K here and subtract K from the subscript, then they'll be the same. So these have just subtracted K from the subscript and then added K to where we start, and then therefore it'll just balance out to the same. So if you expand out, you can show that these two are the same, starting at S equal K. So of course, between the two, the S's can't be the same thing, but the S's mean nothing. They're just placeholders for us to expand back from. So the S, you can call it T, you call it J, for example. It doesn't matter what you call it. It's always going to be the same thing. Once we plug in the numbers, then it's going to give us back the same thing. So hopefully that's clear now to derive the mean, the variance, and the covariance, and the correlation function of an MAQ process. So in general then, if a process has only had correlation up to Q lag, say 3 or 5, then it can be written as an MAQ process then. So that's okay. So then there's notes on the Q test, but there's not a video clip, so I thought that I would do it in the live stream. So the Q test, sorry, there's this this should be L here. So we saw in the lecture, went over in a lot of detail how to do an individual test. We saw how to do the null hypothesis that rho of K equals 0 against the alternative that it didn't equal 0. Well, under the null hypothesis, well, it doesn't equal 0. Under the null hypothesis then, the correlation at lag k is not, and obviously for some k greater than or equal to 1, less than or equal to some higher number, which it's going to be the sample size. We can't, of course, in our sample we can't estimate a correlation bigger, a gap longer than our sample size, because it would be impossible to do that. So we can see then, under the null, if the true correlation is not, then our estimated correlation, rho hat k, and again the formula is given in the lectures, our estimator of k, well, as the sample size gets bigger, should be getting nearer and nearer and nearer to not. And we saw this in the lecture. And what we can show is, if we multiply it by the square root of the sample size, t, that the sample correlation times by the square root of the sample size will converge in distribution as t goes off to infinity to a normal 0, 1. We'll call it z, where z is just the standard normal. Under h0. Under the alternative, well, it will just diverge off the absolute size of it, because it could be positive or negative, will converge to infinity. And because in that case, let's say the true correlation was a half, well, because the sample correlation will get near to a half as t gets bigger, and you're multiplying it by something that's growing with t, then of course it's going to expand, it's going to grow off to infinity. So let's say that rho k equals a half. That means rho hat of k equals a half plus some random variable, call it epsilon hat, which is going to be very small. And then if you multiply both sides by root t, you're going to get root t plus multiply both sides is equal to root t divided by 2 plus square root of t times by something small. So this is going to be diverging off to infinity. So this is why the test works. When the null is true, then this test statistic, square root t times by the sample correlation, will converge in distribution to a normal 0, 1. That means that under the null hypothesis, 95% of the time, it should be between plus or minus 1.96 for t large enough. Therefore, if we observe a sample statistic big, say 4 or 5, then we know that it's highly unlikely that the null could have been true, and we know that when the null isn't true, the statistic will diverge. So that as the sample size gets bigger, when the null isn't true, it will eventually always push us into the rejection region with probability 1, and that's why the test works. So that's just a little bit of a recap of the testing testing a single correlation is not. But what if we want to do a joint test that the first 2 or 3 or 4 correlations are not? Or you may want to test that you can adapt the Q test, and you could just test that, say, the correlation at lags 4 and 5 or not, and we can see how we can do that. But first, let's do the standard Q test. Well, first of all, we've got the null, which is that the population correlations are not for L, where L will be some number, so that's specified by the researcher. So again, you might choose 4 or 8, whatever you want to test. And the alternative is that at least one of them is not. Well, we form the Q stat. Now our test statistic is the sum is this here. And we can see what does this make, why we can take the t out, and we've got this. It's t times the sum of all the sample correlations squared from 1 to L. And as t gets bigger, this will converge to a chi-squared k distribution. And the reason is that under h0, square root t times rho hat of j will converge to, call it zj, where zj is normal, not 1, for all j equal 1 to L. And this follows exactly by this. Just we could do this if each one of these correlations were not, then each individual test statistic will converge to a normal, not 1 distribution. And what we can show is that all of them will be uncorrelated as well. And by definition, square root t rho hat g squared will just converge in distribution to zj squared by the continuous mapping theorem. You don't need to know what it is, but it's just because it's a continuous transformation. If the level converges in distribution to some random variable, then the square of it will just converge to that variable squared. And the definition of a normal not 1 squared is a chi-squared 1. So again, you just need to know the definition. You don't be able to. Well, it's just a definition anyway. And then we then have, well, by the continuous mapping theorem again, we can just take the sum. Well, the sum to here will just be, this will be the sum to, sorry, by Slutsky's theorem actually. When you add them together, they have this distribution, and this by definition is a, sorry, that should be an L, is chi squared L. L is the number of correlations that we're testing or not. Okay, and this, so again, this is by definition the last part. So the key result is a test statistic. As t gets bigger, this q statistic will get nearer and nearer and nearer to a chi squared L random variable. Therefore, we can do a test. We know then that we can look at the distribution chi squared L, and we can get the 95% or the 99% cutoff point and work out what values this q statistic would take under the null with, say, 99 or 95% probability, and that'll be some range like 0 to 6 or 0 to 10. And if your statistic is outside of that range, it's saying that there's obviously too small of a probability to have observed this test statistic if the null was true. Because if the null was true, it would have been in that range with a 99% probability or whatever, whichever you choose. And that's why the test works. We could adapt the q test. Let's say we want to test that row 1 equals row 3 equals 0. Well, that's a bit different to this. It's still a joint test, and we could do the alternative, say that either this doesn't equal 0 or this is an adapt. Well, in that case, well, think about it. What could we do? Well, we can just have, well, if we just take square root t of row hat 1 squared plus square root t row hat 3 squared. Well, it's part of this sum. We're just taking out these two terms under the null. Well, this is just going to converge to a chi squared 2, and so on. So it's the same idea. Under the null, both of them are going to be converging to a normal not 1. Therefore, the square will converge to a chi squared. We've got the sum of two independent chi squareds. So you can adapt the test to test any. You can adapt this test to test any joint hypothesis. If you want to test that legs 1, 4, and 5, say, or whatever you want to do, then you can adapt the test. But the E-views Q test as plotted just gives you the p-value for the null hypothesis that all the population correlations up to that leg are not. So you'd have to do if you want to do this, say, for the project or whatever else, and you have to adapt this test yourself and work it out yourself. Okay? So we've done just a recap of deriving properties of the MAQ. We've done a recap of the Q test. So again, you need to be comfortable describing the test and implementing it and know the formulas and so on. Next part then is just to recap the lag operator, especially around using it to show that an AR process is stationary. So let's give an example. Let's take the AR2 and put it, so there's a step, this is put it straight into its, this has taken yt minus 1 and yt minus 2 to the left. So this is just an AR2 rearranged. So we can write the process in its lag operator form. Again, remember the definition of L is something which, when applied to a variable, it gives us back the lags back. L of yt is yt minus 2, and we call this for shorthand L squared. Again, L isn't a polynomial. There's really no such thing as L squared. It's just taken as defined as LL. So therefore, when you write it like this, technically speaking, it would expand out to that. And think of it like a computer program. So it works from the inside out. So it'll take the first lag, and it'll give you yt minus 1, and then it'll lag it again, and then it'll give you yt minus 2. And again, when you say L behaves like a polynomial, again, L isn't a polynomial. L is not some function which it doesn't equal. It's not mapping. L is not a function from one domain into a range. It's some operator that changes one variable into another. So it implicitly defines, so it's not a function in the usual sense, but it behaves like it is, namely, so we can put it into its lag operator form like this. So these two things are equivalent, and because L behaves like a polynomial, we can rewrite it and we can treat it as if it was a quadratic. So although L isn't a function, it's not a polynomial, it will behave like it is, namely, when we apply either this or this to yt, it will give us back the same thing. So we saw that in the lecture. We gave an example where 1, I think this was it, 1 minus L squared of yt is equal to 1 plus L and 1 minus L of yt. Now if you expand that 1 plus L, 1 minus L, you're going to get 1 minus L squared. So when it says behaves like a polynomial, it means you can do any equivalent polynomial expression and then apply it to the variable and give you back out the same thing. So it doesn't matter whether we apply this or we apply this to yt. They'll both give us back out yt minus 2. And that's what the lecture went, there's a video clip on this as well, and that's what we talked about in the second lecture. So because L is a polynomial, and then gets up the lambda 1 and lambda 2, well this is once you get to here, it's just solving as if it was a quadratic. So you just compare the coefficients and we can find the gamma 1 and gamma 2, gamma 1, lambda 1 and lambda 2 as a function of phi 1 and phi 2. So here it's just implicitly defined. You don't need to solve for them, we know that they exist. They could even be complex, they could be anything, but we know that they'll exist. There'll be some for any phi 1 and phi 2, they'll always exist at gamma 1 and gamma 2 to make the two sides equal to each other. Well, and then we can, all we're doing now is just replace this with the equivalent form of this, and then apply that operation to yt, and that's what we get here. So this is equal to this. And then, so that's it then. And now we can see that if gamma 1 or gamma 2 was 1 or bigger, but let's take the case if gamma 1 equaled 1, which we know which is called a unit root, and we're going to come on to how we test for that in the lecture tomorrow. So if there's a unit root, well, this just means, and it doesn't matter which one it is, 1 minus L, 1 minus gamma 2. Gamma 2 could be anything, doesn't matter at this point. If there's one unit root, well, we've got this, and we can then solve for yt. So first, take this part. So we've got some variable on the right, and then we have 1 minus L to the minus 1 times mu plus epsilon t. Well, L behaves like a polynomial, so 1 minus L to the minus 1, it's just a geometric progression. So it's just 1 plus L squared plus L cubed forever times mu epsilon t. So when we expand that out, we're going to get mu added together an infinite number of times because L times mu equals mu, because it's a constant. So you can think of a constant mu as just a variable xt which takes a value mu in every time period. So when we lag it back, we're going to get the same thing. So we're going to get mu times by infinity, and we're going to get the sum of all the epsilon t's back forever, and the effect of the past will never die away. So if mu equaled 0, then the mean would be 0, so we wouldn't have non-stationarity mean, but even if mu equals 0, we're still going to get epsilon t plus epsilon t minus 1 plus dot 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 back forever, plus, and then we've got the mu part as well. So even if mu equals 0, there'd be a 0 mean, but it's still going to be a function of all the shocks from t back till forever. And when you take the variance, then the variance is going to be infinite. So and it doesn't matter what lambda 2 is. This is just some variable on the left, and this variable is equal to something that's non-stationary on the right. So therefore, when we multiply both sides by 1 minus gamma 2 L minus 1, it's still going to be just some transformation of a process with a potentially infinite mean and an infinite variance, and therefore it will still be non-stationary. Okay, so hopefully that's clear. We covered that in the video clip. So this is it then. And just to remember, for an AR1 model, we're assuming that epsilon t is white noise. So just to be very clear here, all that's left to verify stationarity in an AR model as defined is just to show that the variance of y is finite, because the mean will always be constant, and the covariance function, all that, the key part to show stationarity is just that the process doesn't blow up. So if you show this, if gamma 2 and gamma 1 are less than 0, then that means that it will have finite variance and finite mean, and because the shocks are white noise, then the mean will always be constant, the variance will always be constant, and the covariance function will always be constant. If epsilon t wasn't white noise, if epsilon t was, say, a process which had a changing variance, then it wouldn't be enough just to show that gamma 1 and gamma 2 were both less than 1 for stationarity. That would rule out that there was a unit root, and it would rule out that there was an infinite mean or variance because of that, but it wouldn't change the fact that if epsilon t was, say, some shock which had a changing variance over time, then it wouldn't matter what, it doesn't, even if gamma 1 and gamma 2 are less than 1, the stationarity condition still wouldn't hold. So that's just a key thing to note, is that a unit root, if there's a unit root, then it means the stationarity condition fails. If there isn't a unit root, then it doesn't necessarily mean that the process is stationary. We need then to verify that the means and the variances and the covariances are all the same, and they will be because this shock is a white noise. So hopefully that's clear on the difference between the two. Okay, so then, and again, this generalizes to the ARP. So if you had a YT, if you had an AR3, 4 or 5, all that we'd have in, if you had an ARP, you'd have an pth order polynomial here. You can factor it into its p roots here, and then you would need, again, each one of the roots must be less than 1 in absolute value. Otherwise, it would not be, it would be an infinite variance and a potentially infinite mean if mu didn't equal naught. Okay, so again, you need to be comfortable with the general definition of this and understand the intuition. In terms of practical solutions in the exam, you could technically be given any polynomial order, but of course it's got to be solvable by hand. So of course it does limit, it could be a polynomial of order 4, but of course it's going to be a restricted model. A lot of these coefficients are going to be set to naught, so you can actually solve for the roots. So the algebra wouldn't be too complex if it was an exam question. So let's move on now to the serial correlation and LM test. And again, watch the video clip on this as well, and it's in the lecture notes. So we have our model, which is an ARP. So this is just the shorthand for an ARP, where phi L is the lag operator, which is just 1 minus phi 1L minus dot 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 minus phi P L to the P. This is then a definition of an ARP model. If we expand, so hopefully you can see this. If you expand this out on the left, then we're going to get yt minus phi 1 yt minus 1 dot 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 minus phi p yt minus p, and we can take those p terms to the right hand side. So this is just shorthand for an ARP, and this here is shorthand for the errors being an ARM. So again, there's more details in the notes, but this is an ARM. And again, you need to define these need to be defined here. So this is the phi L is defined as 1 minus phi xi 1 L minus dot 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 xi m to the LM. This will then say that the errors ut from the AR are an ARM process. And remember, you can solve them for the true model. So this just summarizes, and again, because L behaves like a polynomial, so this just says that the shocks ut are no longer white noise. The shocks are actually an ARM, where this epsilon t is white noise. So epsilon t is a white noise process. So we can write yt as a function of ut. So we can just plug in ut, so we can see that ut is just xi L minus 1 of epsilon t, and then plug that in and expand it back out. So we're going to get xi L of yt equals alpha plus this, and then just multiply both sides by xi L, and then we can solve. So we're going to get xi L times phi L yt equals, we're going to get xi. Again, the L will become 1 here, because when we interact L with alpha, we're going to get back alpha plus epsilon t. So all we've done here is show if we've got an ARP model where the errors are an ARM, then when we expand this out, this is going to be a pth order polynomial multiplied by an nth order polynomial, which is going to give us a p plus m order polynomial, which will, this is then just an ARP plus m model. And we showed this in the lecture. If you have an AR1 model with an AR1 error, then we get an AR2 model back out. You can also show this by hand as well, by plugging it in and rearranging it. So you should be comfortable working with it. And again, the benefit of this is that this is a general result for any P or M. So this is a benefit of working with a lag operator here. We can solve this in general as opposed to doing it in each individual case. So this is serial correlation. What that means is then, if we run this regression, again, and remember the regression is going to be here, just to remember for the AR, this regression is just going to be yt equal alpha plus phi 1 yt minus 1. So this, with this model here, this is just the ARP written out. If we run this regression, well, if UT is an ARM, well, first we can see straight away that UT is going to be correlated with the Y, so we're going to get a bias from OLS. But more fundamentally, we've misspecified the model. We're running an ARP when actually the true model is going to be an ARP plus M. This just means we've missed out P minus M lags, and we've got a misspecified model. So we'd get remember the consequence of serial correlation, the errors will be correlated with the regressors, and more generally it means we've misspecified the model. And we can see that by deriving what the true model would be, and now we've expressed it as a function of some white noise shot. When we expand this out, it will just be a P plus M polynomial. We'll get out a P plus M AR model. So how can we test for it then? So the serial correlation LM test is just to test this basically, that the errors have this form, where epsilon t is white noise. So this is the null hypothesis of the serial correlation LM test is that there's no serial correlation. In terms of this model here, it's just going to be that the xi1 equals ... xi m equals naught in this term here. So there's no serial correlation against the alternative that there is. And when we specify an alternative, we've got to specify what the alternative is. So in general, the errors could be some extremely complex process. It could be an AR 5000, say. So we don't know what it is. We've got to make a guess. So we can often be conservative. So we're going to test it against the alternative that if there is serial correlation, that it's of a form of an ARM. So you've got to specify M. So the larger M is, the more general alternative it allows. The downside is you're going to lose degrees of freedom. So this would be that phi 1 doesn't equal naught, and so on, phi m doesn't equal naught. Namely, that there is some serial correlation in the errors. So to do this, we run this auxiliary regression. So this really hasn't got that much of an intuitive, it's got a somewhat intuitive content, but the reason we run this is that under the null hypothesis, t, the sample size, times r squared from this regression, as t gets bigger, will converge to a chi-squared m distribution. So you don't need to prove this, you just need to be able to detail the null and the alternative, state the steps. So you specify this auxiliary regression. You run first off you run the ARP model and you estimate the residuals. These are the residuals from this first regression. So you regress. So you run the ARP regression. Remember, under the null there should be no correlation in the errors. You then get out the estimated residuals, et minus 1, et minus m. So these are the estimated residuals. You then run this next regression where you run the ARP, but now you control also for these estimated residuals here. So the idea being, under the null hypothesis, there is no serial correlation in the errors, so the estimated residuals should be, as t gets bigger, near to the true residuals here, the epsilon t's here. So you're putting these in as kind of a proxy or an estimate for the unobserved residuals, and under the null they should estimate these correctly, because under the null we've got a correct specified model. Under the null the ARP is correctly specified, therefore all the parameter estimates will be consistent for the true parameters, and it means we can then correctly estimate the residuals. So if there was no correlation, then all of these gamma 1 to gamma m should be naught, and that's why the test works. And we can show under the null, and you don't need to be able to prove this, that if we run this regression, this auxiliary regression, and take t times r squared from this regression, as t gets bigger, it will be distributed chi-squared m. Then you can form a test. So again, you need to state the decision rule. So you need to get the critical value from a chi-squared m, So if you wanted to do a 1% test or a 10% test, so you get the critical value. If the test statistic is bigger than the critical value, you reject. If it's smaller than the critical value, you accept. So that's the result. So again, you need to obviously give the detail here, but it's in the notes, and again there's a video clip on this as well. So this is the serial correlation LM test. And another key thing for the project is when you in the project, when you run this, the LM test, you specify M. So as I made clear, if the larger M you specify, then the more forms of serial correlation the test can pick up. Namely, it might be that the errors are in AR4, but if you only test against the alternative that the errors are in AR1, well, you might not reject the null, not because the null isn't true, but because you've not specified a sufficiently general alternative. So that's why there's a trade-off here. The bigger M is, the more potential forms of correlation it can test against, but the downside is you're losing degrees of freedom. So you need to specify M sufficiently large. So again, it's not always, if you don't reject the null, it's not always that the null isn't true, it's just that we've not found any evidence that the errors have the form we specified, this ARM. So if we test against, let's say we do if M equals 3, and we can't find evidence to reject the null, all it means is we can't find evidence that the errors are in AR3, but they could be in AR10 or in AR15 or so on. So that's just something to bear in mind for this test. Okay, so let's just finish off then. I've just taken the slides from we're going to finish with seasonality, and again, if you want, I can do another live stream session if you send topics you want to cover. But let's just go over seasonality again, the slides. So many times when we're presented with data, especially for sales, they have a seasonal pattern. We can see that every year there's this kind of repeated pattern. Even though it's increasing over time, within each year there's a similar pattern. It spikes in the third and goes down in quarter one. We can see this also in the growth rate now. If we take the growth rate, the difference in the log, then we're going to get the growth rate of retail sales. We can see it's around a mean naught, and again there's this pattern repeating every year. It's not the same every year. It's not the same numbers every year, but we can see every year there's the same pattern. It goes up in quarter 3 and down in quarter 1 and so on. So we can see there's evidence here that there's a change in the mean within quarters. So we can see even though the mean overall looks to be naught, we can see that within quarter, that's say quarter 3's mean. If you look at the mean in quarter 3, well, that would just be the average of all these CSA, and that's obviously very negative. And yeah, so you'll be given a chi-square table. So again, you should be clear on. If you're not clear, we can run through that. So you need to be comfortable with finding critical values from the chi-squared table. So what I'll actually do is I'll send out a copy of the tables that you'll be given in the exam, so that you can get familiar with them. So you'll be given all the tables that you need to answer the questions in the exam. Okay, so then we can see very clearly here then that the means look to be changing depending on what quarter we're in. So then this will cause a problem for estimation then, especially when we come to run a var type model. If you think of running a vector model where we've got two variables that have got a similar seasonal pattern, then we're likely to find, for example, a very strong correlation between them, not necessarily because they're related to each other, just because they're exhibiting the same form of seasonality. So if you take retail sales in two very distinct and faraway countries that maybe got even no trade links, you still may find that there's a strong link correlation, there's a strong effect between the two, not because there's any economic relationship, just because they've both got the same kind of seasonal pattern occurring each year. So then you'd find a spurious correlation. That's one reason why we need to remove the seasonality from the mean. Another one is, if you look at the correlogram of this, if you plot the sample correlations here, we're going to get an extremely strong and repeated pattern every 4 quarters going back, not necessarily because there's any kind of economic correlation, but just because the seasonality, the change in the mean is not a correlation, that's a separate thing. So the correlate, when we estimate the mean and subtract it out, we're interested in the deviation around the mean. So if we didn't remove the means from this data here and looked at the correlation, we're going to find very strong correlations that's driven by the fact that we've not accounted for the fact that the mean is changing every quarter. So again, we'd get spurious estimates of the correlation function. So that's the problem then. So it's got undesirable side effects. So we need this is why you often see seasonally adjusted data, which is that especially when we're looking at the effect of one verb on another, we don't want the effects in our vector autoregression models to be polluted by the seasonality. This is why you often are given data in a season adjusted form. And I gave the example in the lecture, even in kind of news reports and so on, they often, when looking at sales growth, they'll often give you the change year on year. So Christmas sales are always higher on average, but they'll look at the difference from this year to last. So if the growth in Christmas sales is bigger or smaller than what the growth was the year before, not compared to the previous quarter. So that's in a way, when you see this data presented even in reports, they're seasonally adjusting how they present it to you, so they don't give you a spurious. It doesn't mislead you, because in Christmas the sales are always going to go every year. But the more interesting thing is how much did it change from last year. So that's in essence is a seasonal adjustment to the data. So there's two forms, and again we only touch on this extremely broadly, so you just need to know the ideas, and there's a whole literature on seasonality. We're just going to touch on this. So the simplest one to understand is deterministic seasonality, where there can be a change in mean, potential change in mean every quarter. So we can see if alpha 1 equals alpha 2 equals alpha 3 equals alpha 0, we're going to get back to the standard model. So he just generalizes the standard model to allow there to be a change in mean every quarter. And this D is a dummy variable that takes value 1. So here, this will take value 1 if T is a quarter 1 observation. So every T, this is some time period, but it could be say T equal 1 to say 100. But if your data starts at say 2018 quarter 3 and it goes on, well that means time period 1 is quarter 3, time period 2 will be quarter 4 and so on. So every T is going to be some particular quarter. So if T is quarter 1, this equals 1 and so on. If T equals 2, if T is a quarter 2 observation, this equals 1, and if T is a quarter 3 observation, this equals 1. Otherwise they're all equal to not otherwise. So we can see then, well, this just says what's the average value of yt given that we're in quarter 1. Well, we can see straight away the mean of this is not always for any quarter by assumption. Well, it's just going to be alpha 0 plus alpha 1 and so on. So we can see we can then have an interpretation of these coefficients. So alpha 0 is the mean in quarter 4, and you can think of this as the base. Alpha 3, 2 and 1 is the deviation in the mean in the other quarters relative to quarter 4. So if alpha 3 is positive, then that means the mean in quarter 4 is bigger than if alpha 3 is positive, that means the mean in quarter 3 is bigger than quarter 4 and so on. So you can write it this way, you can write it equivalently the other way. You can also write it like this. You could also write it alpha d1t plus alpha 2 d2t, and that'll be an equivalent. It'll do a similar thing. You could just add a dummy for each variable and write it this way. So you could do it like this. And what it means by beware the dummy variable trap, if you run it this way, you can't also include a constant. If you did that, then you're going to include the constant twice, because in any time period, one of these dummies will equal 1. So you're always going to include a 1. And you can just think of alpha 0 as a variable that's always equal to 1. As a coefficient on a variable that is always equal to 1. So that's what the dummy variable trap is. If you include a dummy for each quarter, you can't also include a constant, because you'd include the same variable twice. I think it's easier to interpret this way because alpha 1 is just the mean in quarter 1, alpha 2 is the mean in quarter 2 and so on. So you can write it either way, but just be careful to interpret the coefficients that are on the dummies and don't, of course, add in too many variables. So this just plots the correlation patterns, so that sample correlation function for the growth rate in retail sales given here without any adjustments, so it doesn't take into account the fact that the mean's changing. And we can see we've got this when you see this straight away, you can see there's strong evidence of seasonality. It's got a very strange correlation function, and this repeated pattern is coming from this repeated seasonality in the data. So this correlation is not being driven by the stochastic part, epsilon t. It's being driven by these d1t, these constants changing, these shifts in the mean through time, over the quarters, sorry. So we can see that this would, again, if we looked at this would then skew our interpretation of what the correlation structure was in sales data. It does not look like this. So this, again, it causes a misinterpretation of the correlations within, and it would also could cause a spurious relationship between variables in a vector autoregression. So we want to get around this problem. Well, the obvious thing to do is to just run a regression like this. You can estimate alpha hat not 1 and alpha hat 4, and then seasonally adjust. So we just want to remove this from yt. If we of course we need to estimate the alpha. Let's just say we know the constants. If we subtract this from both sides, alpha 1 d1t alpha 4. Well, this is just equal to then the shock. So we can see that once we've removed this, and this will have mean not. Once we've subtracted this to the left, we've now normalized it, call it yt seasonally adjusted. This new variable we've constructed will now just be a mean zero shock around the mean, which is what we want. This is just all the remaining economic variation in the variable around the changing mean. And then we'd want to look at what's the correlation in this, and that's what the next slide does. So in essence, and this is kind of what the news reports do when they subtract out the mean from last year. They're comparing year-on-year means. That's exactly what this does. You're just subtracting out the mean so you can compare them. And once you do this, so you run this regression, again, subtract this part out. So if you run the regression, you'll estimate these coefficients, and therefore you get an estimate of the residuals, and this just plots the correlogram for epsilon hat t. And when t gets large, epsilon hat t is going to be approximately equal to this as t for large. Okay, so now we can see that this doesn't look as odd or unusual. We can see that by around lag 5, there's evidence that the correlations are not, and there's some correlations at lags 1, 2, 3, and 4. So again, looking at this, it looks to be like it's got some AR components, and it looks like it's got an AR. It could be, for an example, an AR1 with a negative coefficient, because we've got this oscillating pattern here. But we can see that if these correlation estimates were near to the true ones, it couldn't be an AR1 with a negative coefficient because they're not dampening down. Namely, if this was an AR1, this would need to be smaller than that. So again, but what this would signal is that there's likely an AR1 component with a negative coefficient, and also some further variables as well. So it could be, for example, it could be an AR, it could be something like this. Or this would be a base model. I'm calling it yt, but I mean the transform variable here. So the seasonal variable yt seasonality, which is just the shock, could be just alpha plus yt minus 1 plus epsilon t. It could be it's epsilon t minus 4 plus epsilon t. And the reason is that, well, this part here can allow, where rho is less than naught, can allow for this oscillating structure here. But then you'd need something else to account for the fact that this is bigger than here. So if you add in this shock, it allows you to change this here. Alternatively, you could do it the other way around, and you could add in both. You could add in a shock for each, and that would then allow this, and so on. So you see the idea that an AR1 term can account for quite a lot of that variation, quite a lot of that pattern, but you need further variables to explain the rest. So that relates really to the project as a bit of an aside to the seasonality. Okay, and again, there's not always a right or wrong answer. It's just the key that you picked out that there's likely to be some AR components, definitely an AR1 component, and possibly some more. It could be some extra MA terms, or maybe an AR2 term, or both, and then that would give you then some candidate models. And again, remember, you've got to do tests, so we can see that there's evidence that a lot of these are not after 5, and there's evidence that lags 1, 2, and 3 is significant. We've got this oscillating pattern and so on. So you need to describe the correlogram, do tests, and then from this make a decision on what kind of models could potentially drive this data. And always bear in mind that there's some true unknown correlation function that we don't know, that we're trying to estimate, and this could be off. So again, remember that just because this pattern doesn't follow an AR1 as is, it could be that it is an AR1 and this is misestimated. That could be this, and that could be smaller here. So again, remember, you can always be wrong. So what we mean is that an AR1 wouldn't fit this graph as it is, but this estimated graph could be quite far off from the actual true correlation structure. Okay. So we've done deterministic seasonality, and this is relatively simple. We just estimate the means and subtract them out, and we've now transformed the model to be a mean zero process in every quarter. So then deterministic seasonality is gone. Another form of seasonality is a bit more abstract, is a stochastic seasonality, where we might think that, again, YT could have already been transformed to remove the change in mean. It could be that when there's high, say, Christmas sales one year, that this could persist even above the seasonal mean, even if the Christmas sales are above its mean that quarter, 1 year, well, that could persist in people's minds and they could buy more next year. That's just one example. That's, I guess, a simplest example to motivate this. But this memory could die away and eventually they'd forget and they'd go back to their normal. Well, you can allow for this by this AR4 type model here. And we've called it a stationary. This is called a quarterly seasonal AR1. But you can see actually it's just an AR4 model where you've set 3 of the first coefficients to not. So this is just defined as a seasonal AR1, namely that where we've just allowed for the seasonality at leg 4. So this is it's just a definition of it. It technically is just an AR4 model. And the problem with stochastic seasonality is, how do you know whether this term is part driving the stochastic seasonality, or is it just part of the economic model? And that's something you can never, it's very hard to tell, and there's a whole literature on this to try and filter out what's a seasonality and what isn't. So it's very difficult to do, but a simple way is just to guess and say, okay, well, we believe for whatever reason that this here is actually coming from a stochastic seasonality, where when there's a shock like period 4, it persists for a certain amount of time, then it dies away. So it just means that we'd interpret that as seasonality. Whether or not it is a different question. So it's a bit harder to understand, but it's just an assumption, and we just believe that this is driving stochastic seasonality. Well, we can actually derive the properties of this model. We did it for the case in, I think, exercise 2, when this was yt minus 2. What we can show is, you can expand it back. So you take the seasonal AR1, you just keep recursing back, plug in yt minus 4 and then yt minus 8 and keep going back, and you'll get this. Well, this has got an MA infinity form where these coefficients, we'll compare them to these coefficients here. We can see that all these coefficients are not, if it's not a multiple of 4 observations, and for the multiple of 4 observations, we should get the phi4 squared. This is just phi4 to the 1, this is phi4 to the 2, and so on. So you just compare the coefficients. All the coefficients are not, apart from on the subscript here, this is a multiple of 4, and this is just the multiple here. This isn't 1 and 2. So if you carried on going, you'd get phi4 cubed epsilon t minus 12, and so on. So you can derive the MA infinity form from this, and then you can just use the formulas. So we can work out the mean, but you can just plug in these thetas into the formulas from the first part of the live stream, and you can work out what the covariance function is. And what we can show is that let's take the case where this is positive, all the correlations are not, apart from multiple 4 observations. So we might believe that when there's a shock at Christmas, say, it persists, and then there's a positive effect next period, for next Christmas, and then next Christmas there's still an effect, and next Christmas there's still a positive effect, and so on. But there's nothing else happening in between. So this might be a hypothesis or a belief of the researcher that there is a stochastic seasonality of this form, where when there's a shock to sales, it persists every Christmas, but it dies away. And to allow for that, Well, you can just specify this model here, because this model will allow for this correlation pattern. You would then seasonally adjust by just subtracting out the seasonal part, the key part being this yt minus 4. If you subtract this out, you get a new, now the shock is everything that's left, and then you look at the correlation here. So in this case, you stochastically seasonally adjust by, once you've done this, you're going to take away all these correlations then from this part here. So once you transform this variable, it will take out this repeated seasonal pattern every 4 quarters. There could still be correlation left. You would then look at what's the correlation left in the shock around this when it's removed all this from it. So that's what stochastic seasonality does, and it's a bit more abstract than the deterministic seasonality. So you need to know what deterministic seasonality is, and to explain it, you need to be able to very broadly explain what stochastic seasonality is, how to remove the issue from seasonality by adjusting, and then the difference between the two forms. Broadly speaking, then, deterministic seasonality is a form of seasonality that never dies away, it repeats every year, and the stochastic seasonality is a form of seasonality that gradually dies away through time. And also, then another difference is that it requires in many ways more assumptions, because how do we know whether or not this part is coming from stochastic seasonality, or is it not just part of the model? We can generalize again. We can in many cases you'll do both, where including all these parts when we adjust. This would take out the fact the mean could change every quarter, and we might believe for whatever reason that these two terms are driving the stochastic seasonality. In that case, we'd run this regression, we'd take out the residuals, and then we'd use this as our seasonally adjusted variable. Once we've adjusted, we've taken out the fact the means change, and we've removed the stochastic variation, which we believe is actually just stochastic seasonality and not part of the economic variation. Okay, so that's it then. So I'll send out the project tomorrow at 2. Possibly could be delayed a little bit, but it won't be much, and it'll be on tomorrow, and I've given an extra week relative to last year, so you've got 3 weeks to finish it, and the details of the format were already available in last year as well. So I'll see you at tomorrow at 9 for the unit root lecture. So bye.